Okay, so today we're learning about rocket propulsion. That's section 6.5 in the book. This is part of the conservation of momentum section. Um, just like I guess the closest thing we had to this earlier was a squid that drives a fluid out of its body to propel itself forward. This is very similar to that in that you have a some kind of a material that's going to be thrown from the system in one direction, which will cause the system to move in the other direction to account for that change in momentum, so that there is an overall zero momentum. It's exactly what we're going for, is the conservation of momentum. So the situation we're looking at here is you have gas inside of a pressurized gas inside of some kind of closed container, and in this case, you have the gas is trying to push outward in all directions in the container. You can see that represented here by these force vectors. And then you just essentially poke a hole in one into the container. And this would be what we would call our nozzle. And on this one edge, you have this force that has nothing to push against here because this hole's been poked in the container. And all these other forces are pushing in the other directions. Well, this force and this force cancel, this force and this force cancel, this force and this force cancel. And you end up with just a force upward on the container in this direction, and the downward force can't cancel it because it has nothing to push against. So you get an overall force upward, which is what causes a rocket to move upward. But in reality, we can treat this as a conservation momentum equation because this downward moving gas that's going to be expelled through this hole in the container is going to carry some momentum with it. It has mass. It has a velocity, so mass times velocity will give you that momentum. And that amount of momentum that is moving that way out of the engine is going to have to be equal to the amount of momentum that the engine that the entire engine connected to whatever it's connected to is going to have going upward. Now, generally, the spaceship or rocket or whatever it is that's moving upward, it has much more mass, and so it has a much smaller velocity for that time. But the interesting thing about rocket propulsion is that the longer the rocket burns, the faster the rocket goes because it is losing mass. The fuel inside the rocket leaves the rocket as it goes out the nozzle, and so the rocket gets lighter, and so the change in momentum actually has a bigger effect on the rocket each second the rocket flies. The equation for this is just like it was before, except that in the initial momentum of the system is going to include the mass of the rocket and the mass of the gas combined into one single velocity. And then at the end of the system, you're going to have separate things. You're going to have separate masses, separate velocities. Here they define all these things. So the momentum of the rocket plus the fuel is big mass of rocket plus change in m, where change in m is the amount of fuel that is about to be burned. And so at the end here, you have the mass of the rocket times v delta v, where v is the velocity of the rocket, and delta v is the velocity of the gas. And here we have delta m and v minus ve, where ve is defined as the exhaust speed relative to the rocket. So the velocity of the gas after it's left the rocket. Where delta v is, let's see, where do they define delta v? Well, delta v is the change in the speed of the rocket as it loses mass. And so here you have the end result of the momentum of the rocket, the mass of the rocket plus its original velocity times its original velocity plus the change in velocity due to the fact that it has expelled some of this fuel out one end at a particular velocity. So we have a slightly different equation, but it's still just momentum before and momentum after. It just gets a little bit tricky. When you solve this equation and simplify it, for the momentum of the rocket, you get m times delta v. So this is the mass of the rocket times its change in velocity. So this is essentially the change in the momentum of the rocket is going to equal the velocity of the exhaust times the amount of mass that has been put into the exhaust. So it's really quite simple in the end. The change in momentum of the rocket is equal to the carried away momentum by the fuel. And that should make sense to us, hopefully. It turns out that the amount of mass of fuel that's consumed as you're firing off this rocket is equal to negative the change in the mass of the rocket itself. And so you can actually make a substitution there, and you can write everything in terms of the mass of the rocket and the change of mass in the rocket. And they actually use a little bit of calculus to solve this equation, so that you can actually get a change in the velocity final minus velocity initial, equal to the velocity of, and that's of the rocket. So velocity final of the rocket minus velocity initial of the rocket is equal to the velocity of the exhaust times the natural log of the mass initially of the rocket divided by the mass final of the rocket. And that mass of the rocket includes all the gas that's in the rocket initially and then the gas that's in the rocket finally. So it becomes quite a simple equation, except we have this natural log. If you don't remember what the natural log is, remember that it is the inverse function to the natural exponent, which is the e to the power of something, right? Where e is the number 2.718, whatever it is. It's the natural number that comes from doing some statistics. But that is the equation you're going to use. The natural log you'll find in your calculator is just ln. And this entire ratio is inside of that function. So you have to do the ratio first and then take the natural log of it, multiply it by the velocity of the exhaust. And you'll be able to calculate the change in velocity of that system, or that rocket. So this is kind of how it works. You have this rocket that's got this mass plus the mass of the exhaust. And the mass of the exhaust is the thing that goes out. That little delta m is the thing that goes out with that velocity VE of the exhaust. So let's go ahead and we can actually calculate instantaneous thrust of a rocket as well. Thrust is essentially the force that is exerted on the rocket. And so if you go back a couple of pages to this representation where we had gas inside of a closed container and then we poked a hole in one side, which was not that far back. Not too far. Anyway, let's go back to here. So if you go back to this picture, you have this container with forces going all directions, and you poke a hole on one side, and that's the nozzle of the rocket. This force that goes upward opposite that force that gets released is what we call the thrust of the rocket. And you'll often hear thrust talked about in terms of pounds in the United States. So, for example, the F-15 has two 20,000-pound thrust engines in it. And 20,000 pounds of thrust is a lot of thrust, and that's why it's such a useful jet for the Air Force still. But anyway, we're going to look at a single, and so, I forgot to mention this equation here, instantaneous thrust, is just equal to the mass of the rocket times its acceleration. Its acceleration is equal to delta V over delta T, and delta V we can actually get from one of the previous equations. And we can make a little bit of a approximation here. We can get delta m over delta t for that times velocity of the exhaust, and get this instantaneous thrust equation. So also they have such things as multi-stage rockets that have multiple rockets within a single rocket, so that one of the stages will fire this rocket up to a certain velocity, and then that stage will detach itself and a new rocket will fire off. And that, of course, just means that you need to do the problem in parts with initial velocities and final velocities that are maybe determined by previous stages. But it's the same math in the end, just used in conjunction with several stages. But the single stage rocket is the one that we're going to deal with now in this example. We have a rocket with a total mass of 1 times 10 to the 5th kilograms, has a burnout mass of 1 times 10 to the 4th kilograms. What that means is that after it's burned all of its fuel, and it's essentially stopped burning. It's why they call it a burnout mass. It's lost. It's gone from 1 times 10 to the 5th to 1 times 10 to the 4th kilograms. So it's lost quite a bit of weight, almost 90% of its weight. And that is pretty typical of a rocket, that most of the weight is in the fuel. It takes a ton of fuel to get something up to orbit. So you have this rocket, it takes off from Earth, and it exhausts all its fuel in 4 minutes flat. You're going to have to convert that into seconds normally, because we're using velocities that are in meters per second. And so anyway, it burns its fuel at a steady rate, so we can assume that there's a steady acceleration. um, or a steady change in acceleration is a better way to say it. And then it has an exhaust velocity of VE equals 4.5 times 10 to the 3 meters per second. So in the part A, they want us to know if air friction and gravity are neglected, what is the speed of the rocket at burnout? So we're not going to include the acceleration of gravity. And that's actually a fairly good assumption to make because rockets are not launched into space vertically, they're actually launched into space horizontally. They go up to a certain height and then they do what is called a roll. So they roll the rocket around and then they pitch it so that it's actually firing parallel to the Earth's surface instead of perpendicular. And the reason for that is twofold. First of all, it's easier to go parallel to the surface of the Earth because you don't have to fight gravity. And the second thing is it's a shorter path, actually, usually that way. So anyway, but it's certainly much easier to do that. If air friction and gravity are neglected, what is the speed of the rocket at burnout? So we're calculating a final speed, a final velocity. Well, that is the equation that we use for the single-stage rocket, including that natural log. So you're just plugging in values. You have an initial velocity of 0. You have a velocity of the exhaust, 4.5 times 10 to the 5th. And then you have your two masses, your initial mass and your final mass. Plug them in, take the natural log, multiply by that velocity of the exhaust, and you get 1.4 times 10 to the 4 meters per second of velocity. To find the thrust at liftoff, you're going to need your delta mass. So delta mass is going to be 1 times 10 to the 4th, 1 times 10 to the 5th. So your burnout mass and your initial mass. Take that difference in mass, and it's negative 9 times 10 to the 4th kilograms, and then you take that and divide it by delta T, and you get negative 3.75 times 10 to the 2 kilograms per second. And that tells us how fast the mass is changing. So that's delta M. And then the thrust is equal to the velocity of the exhaust times delta M over delta T, all inside of an absolute value symbol. Doesn't matter in this case, but anyway, we put all that stuff in, and we get 1.69 times 10 to the 6 newtons. So it's a fair amount of thrust. It's essentially 1 million newtons, which is approximately, let's see, 1 million newtons is about 1,000 newtons is about 200 pounds. So 1 million newtons is going to be 1,000 times more than that, so 200,000 pounds of thrust. That's 10 times the thrust of a really good jet engine. A really good jet engine, like on the F-15, is 20,000 pounds of thrust, and the F-15 can almost reach space. This has 10 times that amount of thrust. Quite a bit of thrust. Find the initial acceleration. Well, acceleration just comes from Newton's second law. Force equals mass times acceleration. And the only kinds of accelerations we're going to have are the thrust and mass times gravity if it launches straight up. And they're going to assume it launches straight up again. So then they calculate that acceleration by just solving for it and then plugging in numbers. It ends up being 7.1 times 7.1 meters per second squared. So in the last part, they want us to estimate the speed at burnout when gravity is not neglected. You're going to use your same equations essentially, but you're going to include this gravity times time, which is going to be an acceleration times time. And you're going to find out how much it accelerates due to gravity and subtract that from the acceleration due to the rocket thrust. And let's see, where did we calculate that before? Oh, so in this case, they're actually multiplying the acceleration times time, so that's the change in velocity due to gravity. And they take that original final velocity from part A, I think it was, and then they subtract this change in velocity due to gravity. It ends up being, I guess, about 10 times less or so. Is that right? Yeah. Not quite. Actually, lose about 20% of your speed.